Thanks very much to the organizers for inviting me. I'm a sort of a new member of the Koopman community. I just really started working on this in the last year and a half or so. So I'm going to talk today about some joint work with Matt Colebrook and Catherine Drisdell. And basically the theme of this work is how to slice up Koopman operators that have a continuous spectrum. So I'm going to focus today on sort of a nice controlled case. So we have a discrete time dynamical system on a d-dimensional state space. As usually, we don't know the dynamical map, but I am going to assume that the dynamics are measure preserving. And there's a technical assumption that they should also be invertible almost everywhere with respect to that measure. So you can think of certain Hamiltonian systems, systems with mixing dynamics on an attractor. And the reason I want to focus on this is because it's sort of a nice relevant class of dynamical systems for which the Koopman operator has a continuous spectrum and some nice spectral properties. So we'll set up the Koopman operator in the usual way. We'll work on the Hilbert space L2, so square integrable functions with respect to the invariant measure. In this setting, the Koopman operator is unitary, and it often has continuous spectrum. I think for reasons that you can trace directly down to certain measure preserving dynamics. So there's been some really nice thread of work on this in recent years. I think it's been known for quite a while that these things have continuous spectrum. There's some very nice work by Igor and his collaborators, bringing in some theory from orthogonal polynomials to do spectral analysis with a continuous spectrum. Some nice contributions from Matt Colebrook, my PhD supervisor, Alex Townsend, and more recently by Demetrius and Claire. So the one thing that was interesting about these works is they tended to focus on Hilbert space formulations, which don't give you a direct notion of eigenfunctions. And if we think about the power of Koopman, I think one of the distinctive features is that you have this beautiful theory connecting the structure of the eigenfunctions to the geometric structure of the state space or the phase space. And so the point of this talk is to try to maybe add a new tool to this collection for the continuous spectrum and show how you can actually define something that looks like eigenfunctions for the continuous spectrum and how you can actually compute them from the usual snapshot data. So these are just input-output snapshots from the dynamical map. So what we like about this approach is it has a rigorous foundation in spectral theory for unitary operators. We do have to go beyond Hilbert space. The algorithms come with rigorous convergence guarantees in the large data limit with sort of the usual assumptions about the data you're collecting. And in practice, the workhorse for these algorithms are some fairly standard variants of EDMD, so measure preserving EDMD in particular, which already have kernelized versions and have been used on very high dimensional problems like coming from molecular dynamics and some fluid flow problems. So the algorithms I'll show you today are already being used not by me, but by people like Alistair Hales at Virginia Tech to study some interesting switching phenomena in turbulent fluid flow. Okay, so let's get to the math. I wanted to start with a simple example, which is sort of canonical in spectral theory. But it also has a nice connection to Koopman. So this is the bilateral shift operator. It basically has ones just above the main diagonal, and it goes forever in both directions. It acts on, didn't want to reveal that yet. It acts on these sort of bi-infinite sequences. You could think of these as like Fourier coefficients. And this has a really nice illustration of the difficulty or sort of the subtlety of continuous spectrum. It's also connected to Koopman theory. So a lot of standard dynamical systems that have this measure preserving property can be reduced to collections of bilateral shifts. So I'll show an example later. So the eigenfunctions of this, if you think about what these are, you might think, well, what sort of vector can I shift? So what does this bilateral shift does? It takes these coefficients of this vector and just moves them up by 1. It takes the jth coordinate or coefficient and maps it to j plus 1th. So if you think about what the eigenvectors for this could be, you'll pretty soon realize that they have to be periodic in some sense. And that the action of shifting them basically corresponds to multiplying by a phase factor. So these are actually basically all the eigenvectors you can find for this particular shift operator. What's interesting here is that the frequency of these periodic eigenfunctions can be any real number between 0 and 2 pi. And so the eigenvalues actually form a continuum on the unit circle. So I'm going to call these eigenvectors eigenvalues. Technically, they're not quite that because these eigenvectors, if you think about what space is this operator unitary on? Where does it have the nice unitary property? It's on the space of square integrable sequences or square summable sequences. This is the right Hilbert space where this is unitary. But these eigenvectors are not actually square summable. They never decay. They just oscillate forever. So these two features sort of go together. When you have continuous spectrum in these unitary problems, you typically have non-normalizable modes that actually don't live in your Hilbert space. So if you want to think about finding them, you have to look elsewhere. You have to look outside of your nice L2 Hilbert space. Your operator is unitary. So again, this is just a simple example, but it's fairly typical. I'll show more examples of measure-preserving dynamical systems where you have this continuous spectrum. And along with that, you have these non-normalizable modes. So I want to, so how can we think about computing a decomposition in terms of these non-normalizable modes? So I know that you all know the usual Koopman mode decomposition, but just to have a reference, I want to get it up on the screen. So just suppose for the moment that we have an observable that's in the span of some real L2 eigenfunctions of our operator. Then any observable in that span can be expanded in those eigenfunctions. It's just a coordinate transformation. The angles are the L2 inner product here. And applying powers of my Koopman operator, I just need to scale the eigenvector coordinates. I just have to power up the eigenvalues along each direction. And then there's this sort of nice form that stacks observables and does the decomposition simultaneously. So this is a really nice way to organize the decompositions for different observables. So I've represented that vector-valued observable in bold here. So these are the Koopman modes. I think of them as the eigenvector coordinates. And we get a nice separability of our operator into some things that depend on sort of time, the discrete time variable, and Koopman modes, which sort of capture the interaction between our observables of interest and the eigenmodes of the Koopman operator. And then crucially, the eigenfunctions of the Koopman operator are what tie us back into the state space. Those are what actually link the operator picture to the state space picture. Okay, so I think these things everyone in this room is very comfortable with. I just want to observe, so for the shift operator, we saw that for measure-preserving systems, for unitary operators, we may not have any non-trivial L2 eigenvectors. So we need to do something more or look elsewhere to find an analog of the Koopman mode decomposition. Okay. So there's this beautiful idea that goes back to Ukrainian mathematician Mark Krein in the post-war period, who basically had this idea. He was looking at differential operators, and he was encountering the same problem where he couldn't find any normalizable modes for them, things like Sturm-Liouville problems, just simple second-order differential operators that come up in mathematical physics. And he had this beautiful idea of looking in a larger space, a space that contains the Hilbert space. And the way that you investigate this larger space is by looking at a smaller space. So you have to pair this Hilbert space with a smaller space of what you would call test functions. And then a larger space, you get with that smaller space, you get a larger space of linear functionals or distributions on that small space. So Krein called this method the method of directing functionals. And there's a series of really beautiful papers about this in the Soviet literature. So a number of years later, Gelfand and his collaborators sort of picked up this idea and extended it to unitary operators. They gave very general conditions under which you could actually find a complete set of generalized eigenfunctions. So not just one or two or a few, but actually a complete set that diagonalize the Koopman operator. So all of the information that's stored in these eigenpairs. So the decomposition, if you have continuous spectrum, goes like this. It looks really natural once you look at it for a few minutes. So you look for eigenfunctions in the larger space of distributions. And you can actually represent any observable in the test space, you can represent in terms of these distributional eigenfunctions. So the expansion coefficients are the action of the distributional eigenfunction on the observable. And then when you integrate over the full spectrum, you combine all these distributions, you actually recover the regularity of the original observable. So you're sort of slicing up this observable. And the nice feature, this isn't just any way of slicing it up. You get this similar analog of the standard Koopman mode decomposition, or the discrete Koopman mode decomposition, where applying the operator to G corresponds to scaling each of the coefficients by a scalar function. Okay, and again, you can vectorize, you can sort of stack your observables. Now, there's one thing I just want to note here in case anyone has seen this before. I'm omitting a sum over possible multiplicities of the eigenspaces. I'm doing that just for clarity because it doesn't play any role in this talk. Okay, but I'm happy to talk about that afterwards if anyone's interested. Okay, so we call this a rigged Koopman mode decomposition. I don't know, it's just seemed natural because you're looking in a rigged Hilbert space. The rigging here comes from the idea of like equipping or rigging a sailing ship. So you're equipping this Hilbert space with some extra structure. And it doesn't have anything to do with ridge regression, because I know I've been approached by people who sometimes say. So, okay, anyways. So what does this look like for the bilateral ship? Just to give a concrete example. So here the test space would be the space of rapidly decaying sequences. So these decay faster than any polynomial in N. If you look at that decomposition of the vector entry-wise, if you think of these the observables entries as Fourier coefficients, then its dot product, the action of the eigenfunction on that Fourier coefficient series, is actually just a Fourier series, and its coefficients decay very fast, so it's a nice smooth function. And then when you integrate over the spectrum, you actually are just so you're actually just integrating again against the kth eigenfunction, generalized eigenfunction. And this is just a computation of the Fourier coefficient. So this is just a statement of the orthogonality of Fourier series, how you recover the coefficients. Okay, so these are your generalized Koopman modes. For each theta, you get a nice scalar value. You're just evaluating the Fourier series at theta. If you think about applying the Koopman operator, you're shifting the Fourier series up. This is equivalent to just calculating the k plus nth Fourier series, Fourier coefficient, which is exactly what you would expect if you shifted those coefficients up by k. Okay. Any questions on this example? So now I want to talk about how you compute these. How do you go about computing distributions or linear functionals beyond a Hilbert space? Sometimes we have enough trouble just approximating functions in a Hilbert space. Why do we want to go and get these? How are we going to go and get these generalized eigenfunctions? So the basic idea is to approximate them from within the smooth test space. So approximate them here by rapidly decaying sequences and trying to build those up into these exponentials, into these non-normalizable nodes. Okay. So the basic idea here is borrowed from numerical linear algebra, this idea of filtering filtered eigensolvers to speed up convergence and things like the power iteration. That's sort of where my background is from, so that's how I like to think about it. what we have here is just a filtered operator K. So what have we done? We've applied a filter function to the spectrum whose job is to be very, very small away from the mode that we want. So it's basically its job is to damp out all the unwanted modes and to preserve the contribution from the target modes. On the other side, we actually get an operator out of this. We're building this observable by filtering out the contributions of these unwanted modes. And so I want to think about this in sort of two ways. On the right-hand side, I'm going to think about a scalar filter that I can apply to the spectrum. And that's where I'll get all my theory from, my analysis. And on the left-hand side, I'm going to have an operator that I actually want to compute from data. I'm actually going to try to compute those observables, filter out those unwanted modes by computing this filtered operator from data. Okay, so the scalar filter, just to illustrate the idea, you can think about the Poisson kernel on the unit disk. If you plot it as a function of the angle, 0 to 2 pi, you'll see that it's localized around theta equals 0. So you can shift it to be localized near other modes. And as this parameter epsilon goes to 0 or r goes to 1, this becomes very intensely peaked around 0. This approximates a direct delta. So the idea is it's picking out the value of that integrand at the target mode. Okay, we have to be a little bit careful about convergence, but I'll talk about that in a minute. Okay, on the left-hand side, we have our filtered operator. How are we actually going to compute that? So you can express the operator, the Poisson filtered operator, as the jump in a special function called the Caratteidori function, which you can think of as a proxy for the resolvent, really. And the picture here is really over here on the unit circle. If you evaluate this Caratteidori function just outside the unit circle and just inside the unit circle, and you look at the jump as you pinch down, as you take epsilon to 0, this operator valued function is dominated by the eigenmodes near that angular frequency. So this is what we would call a unitary analog of Stone's formula, which uses a similar idea on the real line for self-adjoint operators. Okay, so I'll talk about convergence as we pinch down in just a minute, as we take that limit epsilon goes to 0. But first, we have to figure out how to compute these Caratteidori functions from data. So the basic setup is we have our snapshot observations, and we have some dictionary of observables. And the idea of, I think, at least the standard versions of eDMD can be understood as a best fit or a projection from an infinite dimensional space to a finite dimensional space. So for example, if you took eDMD, you'd basically be looking at like the best L2 projection onto the data. And if you do that with a bilateral shift operator, you won't get a 3x3 Jordan block, but just to illustrate, you'll get a Jordan block. And this has all of its eigenvalues at 0. The Caratteidori functions of the Jordan blocks converge outside the unit disk, but they don't converge inside the unit disk. And so you can't use them to approximate the jump across the unit disk. So that's where MP-EDMD comes in, measure preserving EDMD. So this was, I think, a maths idea inspired by an idea of Peter Badu, who had done some very nice versions for DMD, measure preserving DMD. And basically, the idea is just to find the best unitary fit to the data instead of just doing an L2 orthogonal projection. So here, you would get, instead of a Jordan block, a circulant matrix whose eigenvalues live on the unit circle. And you can show that in the limit of large data and large dictionary, that these Caratteidori functions, that the MP-EDMD approximations actually converge in the strong topology. So that's how you compute the Caratteidori functions, how you compute these filtered operators. What about the right-hand side? What about the analysis? What can we say about convergence as we evaluate the Caratteidori functions closer and closer to the unit circle? So let's just think about the Poisson case for the moment. this is just a nice scalar filter. And we can say something like the following. We can actually get rigorous convergence results. So if you're, I haven't said, so rho g here is just a normalizing measure, sorry. So typically like on absolutely continuous spectrum, this would just be a nice continuous density. There are some exceptions to that, but in practice, it's often continuous. So basically what you can say is if this normalizing measure and the generalized eigenfunction coordinates are sufficiently regular, if they're Lipschitz continuous, for example, then the approximations that come from your filtered observable converge in distribution, in the sense of distributions, to the actual generalized eigenfunctions. So their inner products basically converge, if you like, to the dual product with the actual generalized eigenfunction. The R phi here is just a normalizing factor, so you converge to a scalar multiple of the generalized eigenfunction. Okay, so you can actually obtain rates. For the Poisson kernel, you will never get better than epsilon log epsilon as you pinch down. So it's a sharp estimate, but it's a slow rate of convergence. The problem here is that you need to take epsilon very close to the unit circle. You need to evaluate the Caratio-Dori function very close to the unit circle. And if you want to do that, you have to evaluate the resolvent. And evaluating the resolvent near the unit circle requires more and more data and more dictionary. So you have to expand the dimension of your MPE DMD problem. So I'll just say quickly, you can design better filters, for example, by taking careful combinations of Caratio-Dori functions. So this is just a plot of some higher order kernels. You can see that they're more peaked near the variable of interest. So the blue case would be the Poisson kernel, and then you would have higher order generalizations. You can get a similar theory as for Poisson. You get convergence and distribution with some regularity, but now the higher order kernels exploit additional smoothness in the generalized eigenfunction coordinates, which again, in practice, we often see that these are like infinitely differentiable, except at a few exceptional points on the spectrum. For example, where the multiplicity of the generalized eigenspace changes. Okay, so just to show the sort of effect in practice, this is for a simple dynamical system, the cat map. It has continuous spectrum, except the trivial eigenfunction associated with 1. The lines are basically increasing order of kernel. And what you can see is that you can get much higher accuracy in your generalized eigenfunction coordinates as you refine epsilon down. So sorry, this axis is epsilon, how close you are to the axis, and this is the error in smooth generalized eigenfunction. So basically what this is saying is for a fixed epsilon, for a fixed amount of data, you can improve the accuracy of your approximation by using higher order kernel. Okay, so let me finish with just sort of 2 simple examples, which I think represent what sort of information you can start to extract from these eigenfunctions. So this is a pendulum, a nonlinear pendulum. It has a continuous spectrum, except at the origin, where it has this nice eigenfunction. And if you sort of go along the continuous spectrum and plot the generalized eigenfunctions that you get, you find something very beautiful and maybe not unexpected if you've spent a lot of time looking at Koopman eigenfunctions, which is that these really are singular eigenfunctions. They're non-normalizable. They're measures with a singular support. Their support is concentrated along the lower dimensional subset of the state space. And they actually concentrate along the level sets of the Hamiltonian. And then you can also sort of reason about what we've plotted as the color change or the phase change as you move along the level set, being associated with different subspaces or frequencies or energies. So this is Hamiltonian systems, and you can actually see that this is a general property. So in the paper, which I'll link at the end, you can actually write down some analytical expressions for these types of eigenfunction expansions for general integrable Hamiltonian systems. If you have action angle coordinate representation for them. So you can do it in terms of the radon transform. Another type of example would be something with like a mixing phenomena, like the Lorentz attractor. So again, we have a continuous spectrum except at the origin. And you see these spikes, which you can think of as corresponding to resonances. So if you look at the transfer operator picture, you might expect just inside the unit disk to see some eigenvalues associated with modes that decohere slower than expected. So you can think of this as like constructive interference among the generalized eigenfunctions near these modes. So you can start to use these for constructing reduced order models. You can use like a quadrature in the generalized Koopman or the rigged Koopman modal decomposition. So these are some nice experiments that Matt did showing sort of the coherence or the invariance of the approximate, the computed eigenfunctions for different kernel orders relative to the epoch. Okay, so as you increase kernel order, you get better invariance properties. Okay, so with that, I think I'm a little over time, so I'll say thank you, but happy to talk more and take your questions.